Hello, welcome back to this video. So in this video, I'm actually just doing sort of a what do you call that? Some analysis on square wave waveforms. We are doing a summation of several frequencies. So last time we were talking about summation of sine waves. Now we are going to do summation of square waves. And let's take a look how the waveform differs a little bit. Yeah. So this is what we have. Okay, our summation of frequencies. Okay. And let's see where the things goes. It should be written somewhere. Okay, right measurement to summation of frequencies. Okay, sum of frequencies.lvm. Oh, in the desktop. Okay. So I'm going to the desktop and let's look for sum of frequencies.lvm. This was just done a few minutes ago. Sum of frequencies. Yes, so this is the square wave looking thing. So it will not it will vary between 13 and 17 in some integer values. Well, not exactly integer values, but discrete values. So I'm going to open this up with calc. I'm going to save it as the CSV file inside let's see. Okay, 1e minus 3 hertz square wave. SQ wave. Okay, CSV format, and I'm going to there should be some 13.8 or something down. 13.8, yes, down the line, and that's where we are going. Now I'm going to put this in the MATLAB. Okay, you can of course use your own code, but I have my in-house code, which I also describe how it works. Sum of frequencies, I'll put it here, and I'll copy this and I'll paste it here. Square wave. Okay, so now notice this thing actually looks a little bit different from the sine wave, but most of your frequencies are also present there. Okay, so let's take a look over here. Now this is one sort of a waveform. Okay, 1 times 10 to the minus 3. Okay. Yeah, so we expect at 1 times 10 to the minus 3 to have one sort of peak, 2 times 10 to the minus 3 another peak, 4 times 10 to the minus 3, 8 times 10 to the minus 3, and 16 times 10 to the minus 3. Okay. Okay, now you can see the amplitudes are more or less the same. Okay, of course we have secondary peaks here. Now 10 dB below, which is I think about 10 times smaller. Okay, so not 10 times smaller. Okay, so this is minus, all of these are minus 6 dB. This is at a minus 10.8 dB. So it's about 3 dBs, 4 dBs down, 4 to 5 dBs down, decibels. So it's not exactly 10 times smaller, but it's much smaller than all the waves here. So you can see at least inside the from this graph you can see that the signal pattern is more or less the same whether you use a summation of squares or a summation of sines. Of course, ideally we will have more data, but I only filled it up to 1000 seconds to save time. Okay, that's one oscillation of the lowest frequency, 1 times 10 to the minus 3 hertz, one full oscillation. But yeah, it works otherwise. It sort of works. Okay, so you can see the summation of square waves and the summation of sine waves actually works. Okay, again, if let's say you have this problem where Okay, if you have this problem where your controller is not able to follow a nice sine wave or even a multiple square wave value like this, what you can do is to approximate this whole pattern as a binary signal. Okay, approx as binary. So what does it mean to approximate as a binary signal? Okay, so to do that, what it means is this: if you have your square wave like this, okay, so you have this sort of a really weird pattern, right? Okay, so to approximate as a binary means if this is 0 and this is 1, this is -1, okay. Okay, so this is a very common signal used. The binary signal will be you take any value above 0, you approximate as a 1. So any value above 0. So if this is 0.5, for example, 0.6, 0.7, 0.8, all of these values are above 1. You just increase the value to 1. If the value of the value falls below 0, okay, it will all be made up to -1 here. Okay, so your binary signal, okay, your binary signal will be over here. Okay, your binary signal will be over here, this red curve, and the normal signal will be this green curve. Okay, now how is this being done in LabView? Okay, so the sum of binaries sequence can be over here. Okay, I'll open up the subsystem and I'll show you some of the results. So this is the subsystem that does a binary sum of frequency, binary approximation. So what I do is that I have a sum of frequencies here, sum of frequencies Vi here. What happens is that okay, what happens if, let's say, the value is 0.5? Okay, the value is at 0.5. The way to get it, to get a 1 value, is actually you take 0.5, divide by 0.5, and that will give you 1. Okay, and if your value is below 0, what do you then do? If let's say this is minus 0.2, well, you get minus 0.2 divide by 0.2, and that will give you -1. And this is basically how you convert any waveform into a binary signal. Okay, you take the value and then you divide by the absolute value of that. Now there's a third case. It happens sometimes. Okay, it happens sometimes. You don't just get values above and below 0. Sometimes you get a value of 0. So if let's say you have a value of 0 here, okay, if a value of 0, if you use this same algorithm, 0 divided by the absolute value of 0, you have a 0 divided by 0 problem, and LabView will just give you something called NaN, or not a number. Now if you have a NaN problem, what then do you do? Now you can just set this to -1 or 1. It's really up to you. You just do this kind of manual setting. Okay, so I for one like to just set it to -1, but just so that these NaN values are here. So okay, so this is what the thing is like. Okay, I have the VIs. I'm using the sum of frequencies virtual instrument VI, and again I will have all this going on behind the scenes to give you a sum of frequency signals. The only thing I need to change is to, okay, well, I have to do a little bit of a thing. Okay, I have to minus the offset first. Okay, oops, sorry. Okay, I have to minus the offset. Okay, because why? this algorithm doesn't quite work all the time. If let's say I'm actually varying, okay, I have a sine wave varying between like what, 15 and maybe 13 here. Okay, if I take 15 divided by 15, it's 1. If I take 13 but divide by 13, it's 1. So I have to convert this signal into a sine wave that varies between like what, 1 and -1. So this middle value is 14, so we have to subtract 14 out first, and that is no, not a good color here. Okay, that is -14. Okay, so I have to -14 to here, and that's how we do it. Okay, so we have to subtract off the offset. So the first thing I do is to subtract off the offset, and then I'll add it back later. Okay, so once I subtract off the offset, I will I will wire into this thing here. Okay, I'll wire it into this thing. This thing here is actually, just find the absolute value. Okay, where's the absolute value? Yeah, absolute value. This is the one. Absolute value. Okay, so again, you right click, go to numeric, and you will see this absolute value thing here. Now I have not corrected it to try to account for this 0 divided by 0 problem, so I'll just do it now. Okay, but anyway, before I continue, so I take this, the value of whatever the sum of frequencies output is, of course minus the offset, and I divide it by the absolute value to get either 1 or -1 thing. After I get a -1 or -1, okay, assuming I solve the 0 divided by 0 problem, okay, I will then multiply it by the amplitude. Okay, I will multiply the 1 or -1 by the amplitude. So if my amplitude is 2, it will vary between 2 and -2. And this last part is to add back the offset. So if I were to want to vary between 13 and 15, okay, so 13 and to vary a sine wave between 13 and 15, I will need a sine wave varying between 1 and -1, and then I add 14 to it. So I'm adding back the offset at this last part. Okay, so let's try and tackle the 0 divided by 0 problem. So I never want this absolute value thing to actually divide by 0. Okay, so one way is to set that value to -1 or 1. Okay, so if we have a 0 divided by 0, this enumerator will be 0. The denominator can be anything except 0. So let's take that out. Okay, so what I'll do is I'll use a case structure here. A case structure is basically an if statement, basically. So if this value is 0, what will happen? Okay, so let's do a comparison. So I want if this thing is equal to 0. So you go to comparison, you have this thing is to test whether it's equal to 0. So if this thing is equal to 0, okay, I will just wire into this true or false statement thing here. If this is equal to 0, I need it to output a value of 1. Okay, because 0 divided by 1 will still give me 0. So okay, I'm not going to set the thing at 1 or -1. I will just give it a 0. Okay, so that's close enough for me. Okay, so let's give it a numeric constant, and we will just put 1. We will wire 1 into the output. Okay, okay, that's 1. Okay, if it's false, if it's not equal to 0, I will just wire the input through. Okay, so again, if this thing is equal to 0, I will just output a 1. If it is false, I will input whatever value out there. Okay, whatever value is right. So this is the case structure I want to avoid the 0 divided by 0 problem. because that has happened before. Okay, so there we go. That deals with the 0 divided by 0 problem. Okay, deals with 0 divided by 0 problem. Okay, and what we have then is a binary output. Okay, so this is how the binary sum of frequencies thing works. I use the previous sum of frequencies and convert it into a binary signal using this part here. Now I'll just close this thing. Okay, so this is how the sum of binary sequence actually works. Okay, let's take a look at the some of the results. Okay, I might or may not have a 0 problem. Let's take a look. Okay, sonar.n. Okay, let's take a look at some of the test data. Okay, binary sum of sequences here. Okay, so this one actually changes the value between 17 and 13. Okay, so I will open it with Excel. Okay, this one actually has a not a number problem. Can you see NaN over here? So actually, let's get rid of the not a number, and then we'll just replace all the not a numbers by 15, which is the middle value. Okay, so let's do a data auto filter, and let's change it to those all with a not a number. So there are many times where we have this not a number problem. The only thing we can do is to replace all of this by the number 15. Okay, so we'll just replace all of this by the number 15. Okay, if not, we'll have some error. Okay, so let's put it all, and we'll take off the auto filter. Okay, so this first column is the binary signal. I actually want to superimpose it on the sum of frequencies signal. Okay, I'll save as a CSV. Sum of frequencies binary sequence square wave 1e minus 2 or 1e minus 3 hertz. So let's take the square wave signal, which is over here. Let's open with LibreOffice Calc. Oopsie. And then we will put this into our MATLAB. Okay. So let's take a look. So let me do square wave. Okay, multi-frequency, binary versus normal signal. Okay, or let's put original signal. Yeah. So we have binary versus original signal. Okay, so we have two waveforms here. The binary signal will be the blue one, and the original signal will be in orange. And it's nice that we can see them side by side, so we can see what's the effect of doing this binary thing. Now I want you to notice the key frequencies that we need are still there, and they're still the strongest signals. You can see that even if we do binary, okay, we do binary, so the smallest one is what? 1 times 10 to the minus 3 hertz. Next is 2 times 10 to the minus 3 hertz, 4 times 10 to the minus 3 hertz, 8 times 10 to the minus 3 hertz, 16 times 10 to the minus 3 hertz. And then there's of course a lot of other signals in the background, okay, which are much lower. as you can see, there are at least, you know, about, okay, this is minus 2 dB, this is minus 3.5, the next strongest will be minus 6, so it's about another 3 dB down, okay, another 3 decibels down, where you actually have all the other peaks. Now if you want to just isolate these signals, I mean, this is good enough. You have your 5 strongest signals here to be your main signals to which you want to test. And by this, I want to, like, you know, make the point that, you know, even if you use this binary approximation and you compare it with the original square wave signal, this is actually pretty good. And we already shown that, you know, the original square wave signal and the original sine wave signal, they are actually pretty similar enough. So, I mean, if you want, I mean, actually, you know, it's a good idea, I think, to have the 1 times 10 to the minus 3 hertz sine wave and 1 times 10 to the minus 3 hertz square wave together. So let's do this. Look at this, the square wave. Okay, we have a square wave. We have a square wave signal. We can compare it with a sine wave. Okay, versus sine wave. Okay, so I just want to show, yeah, the square wave versus sine wave. So let's look at, yeah, inside here we just have square waves, so we need the sine wave as well. Okay, the sine wave goes all the way up. Okay, let's open this up. Square wave only goes down to 1000 seconds, which is fine. Okay, oh, let's get the sine wave part out again. Okay, and everything at the bottom we'll just delete. Okay, I'll use the text CSV format. I hope this works well. Yeah, but this is pretty much what I'm doing. You know, comparing the sine wave signal here versus the square wave signal. Now, of course, we've shown that the binary and square wave signal is already pretty similar. Okay, and let's compare the sine wave and the binary signal. So again, you can see that the waveforms are very different. The square wave is in blue, the sine wave are in, you know, orange. Okay, but the strongest signals are over here. As you can see here, the strongest signals of the sine wave and the strongest signal of the square wave, they are pretty much the same. Okay, they are in the same so-called dB range, decibel range, and they are higher than of course all the surrounding noise over here. Okay, so if you don't mind all this noise, and this noise is actually like what, minus 10, 11 dB and such, so don't really have to worry about them. This is like minus 7, minus 6 dB. Yeah, so it's pretty much a good way to, I mean, using square waves is a good way of doing things. And if you want to use a binary sequence, okay, binary versus original, you can as well. And if you do a fast Fourier transform and you look in the decibel range, okay, the square wave, okay, the square wave is over here, and they all show the strongest signals will always be this these original signals which you put. So that shows you, you know, if you want to do a binary type signal and a square wave type signal and a sine wave type signal, they are more or less, they have the strongest frequencies at the frequencies that you want. Okay, so I did show you some algorithms of binary signals, the multi-frequency binary signals, and we look at the comparison between the sine waves, the square waves, and the binary signals as well. You can see that the binary signals is not too bad. It's a pretty good approximation. Okay, at least when you look at the Fourier transforms of them. Okay, so that's all I have now. I'll continue more discussion in the next video. So thanks for watching.